Good morning, good afternoon, or good evening, depending upon when you watch this video. Today I want to work a motion problem for you, and this comes from our textbook on page 93, problem number 11. I appreciate that you don't have your textbooks in front of you, so I'll read the problem to you. According to a newspaper account, a paratrooper survived a training jump from 1,200 feet when his parachute failed to open, but the parachute provided some resistance by flapping in the wind as he fell. Allegedly, he hit the ground at 100 miles per hour after falling for 8 seconds. Test the accuracy of this account. Assume a terminal velocity of 100 miles per hour. Calculate the time required to fall 1,200 feet. So that's our task. We want to test this claim, and I've sort of outlined what we need to begin at the top of the graphics tablet page. So he did a jump from 1,200 feet. So the altitude, y, at time 0 would be 1,200, and the units would be feet. It's also an important piece of information here that the terminal velocity is given, and that's given as 100 miles per hour. Now, since the altitude is in feet, and I'll be using gravity as 32 feet per second squared, we need to change this terminal velocity into feet per second. And so with the calculator, I've just used conversion constants, and I find that his terminal velocity, as given in the textbook, is 146.67 feet per second. Then the claim is that he fell for 8 seconds, and the suggestion in the book is we test this part of the claim, that he fell for 8 seconds. So why don't we get started here and see what we can make this thing look like. There are a couple forces involved here. There is a force of gravity, which is attracting him to the earth, so that would be Fg, and then he's getting some resistance from falling, resistance to falling, Fr, which is known as air resistance. Okay, so Fg and Fr are the two forces acting upon this person, and we can quantify these. Fg would be negative mg, where g is the acceleration due to gravity, and negative because this force is acting in a downward motion or downward direction. And Fr, the resistance, somewhere in the textbook it said to assume that this is proportional to his velocity. So Fr is kV. Let's be careful of the signs here. The Fr would be acting in the positive direction. His velocity would be toward the earth, downward, so the velocity would be given a negative sign, and in order to make the force Fr positive, we would need to put a negative sign on this equation. K will be a constant, and almost always we take these parameters to be positive values. So K will be a positive constant, and more about that in just a second. So the total forces acting upon this paratrooper would be F, and that would be the sum of the individual forces, Fg plus Fr, or negative mg minus kv. Now we know that force, from Newton's laws of motion, we know that force would be ma, so this would be m. We'll call that ma. But this is the acceleration, which is the derivative of the velocity. Acceleration is the derivative of the velocity. So if we first divide through this equation by the mass, I get that the change in velocity, dv dt, that would be a, is equal to, and dividing by m, the m's cancel out, negative g, and then minus k over m v. Now we can rewrite that just because it would make it maybe easier to visualize what's going on here. So this would be v prime is equal to minus k over m v minus g. And a substitution, just to make it easier, would be to let rho equal k over m, and then write v prime equal negative rho v minus g. Now when I look at this differential equation, I see that it is falls into two categories. If I would transpose the rho v term, it would become v prime plus rho v is equal to negative g, which is the form of a linear, first order linear equation, and I could find an integrating factor and solve it that way. But it's also a variable separable, so some equations fall into more than one category, and I think we've mentioned that before, but I don't know that we've really looked at one that fell into more than one category. This one does, and maybe the easiest way to solve this would be to see this as a variable separable equation. And if we do that, I would rewrite it as 1 over rho v plus g dv is equal to minus dt. And so you would integrate that, and this is going to be a log with appropriate variables added in. I mean, if this is 1 over u du, the du would have to be rho dv. So I'd put in a row and divide by row and so forth, and we would get, after very, very little work, we would get v is equal to c, a constant, e to the minus rho t minus g over rho. And this is a general solution because it has an arbitrary constant c in it, but we know that we have an initial condition, and the initial condition would be that the velocity, the downward velocity at time 0 would be equal to 0. The parachutist jumps from an airplane, and the airplane, when you jump, is easily assumed to not have vertical motion. It's not going up or down, it's flying straight and level, and you jump. And so this velocity would be the vertical velocity, and that would be 0 at time equal to 0. And so using the initial condition, we would get a v is equal to g over rho e to the minus rho t minus 1. So that's the first step. Now we've got a little more work to do. like we'd like to evaluate this rho. We know rho is G over K, but not G over K, but rho is, where did we assign rho? Here. Rho is K over M, and M would be the mass of the parachutist and his parachute. We don't know what that is, and K would be a constant, a parameter, but we don't know what that one is either. This would have to do with his form factor as he falls through the sky, and we don't know that. But we can evaluate rho from this equation right here, because we know that he is going to reach terminal velocity, and we can calculate what the terminal velocity would be. In fact, we know what the terminal velocity is going to be. We're given, and that's what makes this whole thing work, we're given the terminal velocity. Now, what is the terminal velocity? Well, the terminal velocity, Vt, is velocity when Fg is equal to Fr. When the force in this direction is totally counterbalanced by the force in that direction, there will be no net force, and the object will not accelerate anymore. That is, its velocity won't change. It'll maintain the velocity it has, but its velocity won't change. So that is why we can write. So we can set Fg equal to Fr and solve for V. So this would be minus mg is equal to negative kv, or V, when these things are equal, then the V would be Vt. So V, I'll put a little t on it, but I'm just going to solve this for V. So V is equal to m over k g. So Vt is g mk, or m over k times V. So that's kind of a nice result. And we can make it even a bit nicer using the previous substitution. M over k is rho. So if we do, or k over m is rho, k over m is rho. So this is 1 over rho. So this would be g over rho. And just a reminder, that's the terminal velocity. And just another reminder, that's equal to 146.67 feet per second. And this is given in the problem. So where is all this taking us? This is taking us to G over rho is equal to 146.67. Therefore, rho is equal to 32 divided by 146.67, and is equal to 0.2181, at least to 4 decimal digits. So now we've solved for rho, and then working back just a tad, we would have v of t, the velocity, is equal to the terminal velocity, e to the negative 0.2181 181 t minus 1, using a relationship from the previous page. And we know what v of t is. So we also know that v of t is y prime. So y prime is equal to vt, don't forget that's a constant, minus 0.2181 t minus 1. Then can we get a function that tells me what the altitude of this falling parachutist is? Well, I just solved this differential equation, and this is a differential equation that is variable separable. Since v sub t is a constant, really the only variable on the right hand side is t, appears right here, and the dy is the only variable on the left hand side. So the integral of dy would be y, and that would be equal to vt integral e to the negative 0.2181 t minus 1 dt. And how much can I skip here? So do this integral, and I'm going to let you do that. I'm not going to write down what all that is. And use y of 0. Now what's the altitude at time 0? Well, it's given in the problem that it's 1,200 feet. So this is an initial condition. Whenever you solve by integrating, you're going to pick up an arbitrary constant. You can use this initial condition to evaluate the arbitrary constant, and we will get y, after some algebra, y is equal to minus g over rho squared e to the minus rho t minus g over rho t plus 1872.73. So this will be the value of y after you've used this initial condition. And I've gone back just for the ease of writing. Instead of using rho equal 0.2181, I've just used the rho symbol again. And this is what y looks like. Now, the question that we were set to answer is, how long does he fall? Well, the newspaper says 8 seconds. But we would find that out by looking at when is y of t, that is, when is his altitude, equal to 0. That's the value of t that will tell me how long he fell. So I'm going to set this equation for y, I'm going to set it equal to 0 and solve for t. Now, that's going to present a problem because I've got t appearing as an exponent, and I've got t appearing as a linear factor, not exponentiated, but just as a t down here. So that's going to be a problem, but not too big a problem today. I don't think I'm going to write that out again. Maybe I will. So 0 equals negative g, that's 32 rho squared, we know what that is, e to the negative rho t minus g over rho t plus 1872.73. How do we solve this? Well, I'm going to just give you easy ways. One is use solve on your Inspire calculator or on Wolfram Alpha, or you could use any graphing problem, any graphing software, but use Desmos and graph y of t and find when y of t equals 0 from the graph. In either case, you're going to find t is approximately equal to 12.5 seconds, which suggests the newspaper was not entirely accurate. They said he fell for 8 seconds. They should have said he fell for approximately 8 seconds, or at least 8 seconds, or more than 8 seconds. But the claim of exactly 8 seconds is not warranted. He fell for something much closer to 12.5 seconds. So that was the little exercise in the textbook. How accurate was the newspaper report? Well, we know it wasn't 100% accurate. Okay, that's all of this problem, and we're going to get started real soon now on linear equations, not necessarily order 1, and that will be a lot of fun, and it will be applicable to many, many different applied situations. So thank you. Have a good day.